Okay, folks, this is a replication study, apparently one of the first replication studies ever in PL, and I'm happy to see such a large audience, if not intimidated. The paper we're talking about today is a paper from PLDI 2017 named Synthesizing Program Input Grammars. Why would one want to synthesize program input grammars? There's a good reason for that. Grammars, you know grammars, right? They have several usages, in particular in parsing and test generation. You know fuzzers that produce lots and lots of inputs. Most of these inputs for complex programs, such as compilers, are invalid. But if you want to get beyond the parser to actual functionality, you need valid inputs. And in order to get valid inputs, well, you can do two things. Either you generate millions of inputs and hope that some of these are valid, or you make use of a grammar or any kind of formal specification to produce them. However, again, I'm talking to the right audience here. Specifying a grammar is expensive. It's not necessarily trivial. So therefore, techniques that allow us to extract grammars from inputs or programs actually help us creating better fuzzers. The idea is you have a set of inputs, you mine a grammar, and then you can use that grammar to run a fuzzer to produce plenty of nice test inputs. My own group and myself, we are invested in that. At 2016, we presented a paper, which is one of my favorites, which analyzes programs to mine input grammars, called Mining Input Grammars from Dynamic Taints. What we do here is we track input bytes through the program execution, and the general idea of all these works is that bytes that are processed the same way actually form tokens. Say all digits of an integer form an integer, and these tokens and structures can then be combined into a grammar that reflects the program structure, and if the parser is reasonably well structured, then the grammar will be well structured just as well. The resulting grammars are highly accurate, and not only are they highly accurate, they're also pretty readable. As you can see in this example, this is a grammar that we extracted from a Java URL parser, and you can see a URL consists of a protocol followed by : / followed by authority, by path, optional query, optional reference. And we even mine these identifiers from the program, so this is the actual raw output of our autogram tool. And well, this is almost textbook quality of a grammar. But then we have a program to learn from. If you want to know how good such a grammar is, you want the grammar, of course, to be accurate, and then there's two measures that you use for computing the accuracy. First, you want your grammar to be precise, which means that we want a high percentage of produced outputs to be valid. And for this grammar that we have over here, it's actually 99.something% precise. The only problem is the host name here. The host name can contain 2 consecutive dots, which, as I understand, is an invalid host name. But other than that, it's pretty precise. But you also want your grammar to have a high recall. Namely, you should accept as many valid inputs as possible. And here you can see that the query in here is overly specific. So this grammar will only parse inputs that contain this exact string as a query. So this query is not perfect in terms of recall. So you want high precision, high recall, and these two are a bit, well, it's difficult to get both at the same time, which is why we have a score, so-called F1 score, which is the harmonic mean between these two. And in order to establish validity, you can either send this to an accepting program, or you have a golden grammar, which you can actually also use to produce test inputs. Golden grammar is a grammar that you define by hand, which you know to be perfectly accurate. Now, this is mining grammars from programs, and well, in a way, this is cheating because essentially it's a nice reverse engineering technique. Much more challenging is mining input grammars from samples, so no program at all. So you don't need program, instrumentation, anything. You just have a set of samples to learn from. And this is a really hard problem. Already in 1976, This was 1978. This was established as an NP-hard problem, even if you have only regular languages. Clark in 2010 produced the best algorithm so far using a minimally adequate teacher, which is essentially a helper that tells you whether an input is valid or not, which can be an acceptor program. And in Angloin and Kharitonov in 1905 showed that even if you do have membership queries, there can be no polynomial time algorithm that actually gets you these. So this is a really, really hard problem, which is why over years there has been a community in formal languages for language induction with well, some progress. Which is why this paper in 2017, when it came along, actually made quite a splash, because it went and said, okay, we want to synthesize program input grammars only from sample inputs and using membership queries, the same thing that we just have found to be, well, hard, but well, you can come up with a set of design choices that make this very feasible for frequent inputs. And what the GLADE tool does is it first learns regular properties, repetitions, alterations, and then recursive productions. And what really stands out is the accuracy of the resulting grammars with F1 scores of 0.9 and higher. This really, really is very, very good. And the whole thing is not only implemented in a grammar minor, but also in a fuzzer that actually was shown to dramatically increase coverage in the same amount of time as AFL, which already at this time was one of the great emerging fuzzers at the time. So this is all nice, and this is all real nice and impressive. One thing, however, that is a bit that when we got access to the paper was a bit complex was we wanted to know what these grammars actually look like. What is their structure? And there's just one single example in the paper about what a grammar would look like. First, the synthesized grammars are too large to show, so this is the one example. And this is an XML example here. So you see there's an XML tag at the beginning, and then there's something, 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 and then there's other sequences which actually go and close the first tag, and then there's more tags openings in here, and then there's possibly more opportunities to close the tag, so the structure of the grammar doesn't necessarily follow what we would consider XML elements, one thing. Second thing, well, there's only one single XML tag in here, namely A, and XML, of course, can have arbitrary tags, and I don't even get into the problem of having matching opening and closing tags here. The GLADE authors provided replication packages 2 times at 2017 and 2019. And these replication packages, you would assume that these allow you to run GLADE on arbitrary programs. That is not the case. It has pretty much hard-coded the 6 programs from the paper. Also, it does not get you access to the grammars that are mined at all. These are saved in a custom serialized format, which is, well, which at least we found in the end impossible to decipher, which also means that we could not get any descriptive statistics on these grammars. And in order to find out what these grammars actually look like, it was no help to us. So what we did then was we took the paper and we went and re-implemented the algorithm. And this was about 6 person months of work in multiple iterations. And the reason why we had multiple iterations is that we were surprised at the results that we got. The grammars that we got were extremely large, and they would essentially enumerate inputs. Here's data from our re-implementation, and you can see that these numbers are very large. For instance, what do we have here? For MySQL, for instance, we have 1,500 non-terminals and 120,000 rules, which is large even for a SQL grammar. And this also tells you that each expansion of any non-terminal in that grammar has about 100 alternatives on average. These are huge, and this is not a problem if you use GLADE as a fuzzer. So as a fuzzer, GLADE works well on them, and I'm very happy to point that out. But if you want to, look at this as from a grammar perspective, this is if you want to parse with these already, this is close to being unusable. These numbers were the first numbers we get. We couldn't compare against any other numbers because these were not discussed in the earlier paper. All we had was the grammars were too large to show. We also computed the grammar accuracy. And here's the accuracy numbers. We went precision, recall, F1 score, and so on. Even with simple grammars, such as palindromes, GLADE didn't fare too well. For the examples that were provided in the paper, we got much lower F1 scores. These are the scores. This is the original picture from the paper. You can see the numbers are not exactly reproduced in here, but you can see that all of these are somewhere in the area of 0.9 and between 0.9 and 1.0. And the numbers that we got for F1 scores are definitely below this. So we don't know how these numbers came to be. What next? Very simple. We shared the results and the code with the GLADE authors, who pointed us to the replication package, and we said we cannot work with the replication package. So then it became, well, that's the problem. We didn't want to debug the replication package, and I'm sure they didn't want to discuss or debug our code, which is perfectly understandable. I have to point out that all this discussion went in a very cautious form, and to the extent of both our abilities on both sides, we did, I think, pretty much everything we could to help the others in reasonable terms. But in the end, we simply assumed that we must be wrong, so we're doing some kind of mistakes, and so this eventually meant that our work had come to a dead end, and that's how it remained for the major part of a year. Then in 2021, a miracle happened because a group of researchers from Berkeley, that's Kulkarni, Lemieux, and Koushik Sen, who's actually also in the room, also did an algorithm that would go and learn grammar from input strings. That's the Arvada tool. This, in contrast to GLADE, would produce small and structured grammars. It's available as open source, and it also compares against the GLADE implementation, so not the paper, but actually against the provided implementation. And while this did not make much of an issue of the numbers, comparing the numbers with the 2017 paper, they also confirmed the observation that we had seen before, namely that the grammars are large and that the F1 score is low. And when we learned about this, then we said, okay, good, now we have independent confirmation of what we thought we were wrong, so we made a paper out of this. And yeah, we submitted this to PLDI, and here I stand. And there you can find all the details in there. When we wrote that paper already, we knew this paper would be, well, difficult to handle. And our, from what we have heard, all the trouble it caused, somebody referred to me, it was as if we had thrown a grenade into the program committee meeting. I don't know about details, this is all confidential, of course, but I would like to point out that the entire handling of this paper, at least from our author side, has been done with the most extreme professionalism, courtesy, everything. So we felt in very good hands, and I'm very happy to say how nice the PL community was to us. So that was very nice. And I'd like to thank everybody whom we caused trouble with. This went up to the SIG Plan Steering Committee, so I'm very sorry that if we have caused any trouble with that. So, what's the takeaways of this whole thing? Takeaways, and this is actually the discussion that I'd like to bring in here. Replication and replicating work is important. It's part of science everywhere, and not only in the CS community, in medicine, and life sciences. Everywhere people replicate work, and that's important. But it's also fruitless, because either you find out that the original results are correct, and then there's nothing new. The fact that there's nothing new can be important in other communities. In ours, it's not so often. Or you find out that something doesn't work, or you find, no, that's not what you find out. You simply find out that your code cannot reproduce the results of others, and then it's actually your job to prove that you're right, and this is a tough job, and you don't know what's coming out of that. And one big question here is, how can we encourage more of these replication studies? Also, what do authors have to supply and support to facilitate replication? And how can we encourage authors to investigate and report the limitations of their work without having to fear that some review too is going to jump directly on that section and copy that into the negative review? There's alternatives, and just a 20-second pitch here. We have done, in the meantime, we have also expanded our work on mining very nice grammars automatically without samples. That's the MIMID work. Just recently, we have expanded this also to semantical constraints, so now we can mine semantic constraints from inputs to appearing at FSE. This year, this is the ISLA work, and we even have a textbook implementation of our autogram work, and I'm happy to, if you're interested in any of this kind of work, yes, we are hiring. And with that, I'd like to close. We've seen the original GLADE work, which, I have to repeat that, was a great contribution at its time. We've seen the GLADE Grammars. Well, as a grammar miner, we can do better than that. We have re-implemented things, and we do have a couple of takeaways. Thank you very much for your attention, and I'm happy to take questions.